Very nice to be back in this very gorgeous place. So I'll talk about dualities, but I only have 2 hours, 1 hour now and 1 hour later. So obviously I cannot do anything very complicated. So my plan for these lectures is to sort of give you a flavor and maybe some motivation why you would want to think about dualities. So dualities really are trying to take a theory which you have specified in one set of variables and find a different set of variables to describe the same theory. Usually there's a very physical picture for what you're doing. Often, at least the cases we look at, the new set of variables actually refers to some topological defects of your theory. Okay, so if you had a superfluid, you have vortices, you can describe that phase of matter either in terms of particles that have formed a Bose-Einstein condensate or in terms of vortices. That's a completely equivalent way of describing the system. And there are advantages of having at your disposal these other variables. Okay. So what I'll do is to make all of this very explicit. The plan is actually to do this in detail for a very simple model. So a quantum Ising model. So we'll be in 1 + 1 dimension, and I'll discuss the dualities of this Ising model. And over here you will very clearly see that we can implement these dualities. Often we can do it exactly. So it'll be the advantages. There'll be it'll be very tractable, and it'll also be very clear why it's useful. We'll see that there is one particular set of variables. We'll rewrite the theory in terms of where the theory will be solved exactly. Okay, so in some sense you have found the right set of variables to describe this model. Those variables are not the original ones, the spins in which you define the model. It's a new set of variables, and there's absolutely no question that it's useful because it actually solves the problem for you in terms of free particles. Okay, so and then I'm hoping to sort of draw some analogies with the higher dimensional dualities rather than trying to derive them. I'll kind of try to point out where they how they're similar, and then finally if I have time I'll talk about topological phases of a simple kind, the symmetry protected and if you like, we'll at least one set of these phases we'll see can be very easily thought of once you have this duality. Okay, there'll be it may be hard to think about these symmetry protected topological phases in terms of the original spin degrees of freedom, but once you allow yourself this freedom of going to dual variables, there'll be a very simple picture of what they are. Okay, so that's roughly the plan, but feel free to interrupt and stop me. But the main idea over here is to give you one very tractable example where you can implement this change of variables, and then we'll try to apply it and try to get some physics out of it. Okay, so before I get into that, so this is really in some sense applying physics to a single model. But let me sort of tell you the bigger picture that we're interested in, which I'm sure many of you are already familiar with, but just for the sake of completeness, what we're really interested in is looking at the quantum phases of a many-body system. Okay, so so it's going to be very important that you have many particles. And this is really the way in which all of this physics differs from the kind of physics you study in your undergraduate quantum mechanics. Okay, so quantum mechanics will play a role, but it's the combination of quantum mechanics and the fact that you have many particles. So for example, you can have some n spins or n fermions, n electrons, and we're interested in the limit of n going to infinity. Okay, and that's really where all the interesting distinctions are going to arise. Okay, so the very important ingredients over here, so we'll have a Hamiltonian, and we'll be interested in the ground state. So that's the to keep things simple, Okay, so this is equivalent to saying that you're interested in zero temperature, you ignore thermal fluctuations. So all of the physics over here is controlled by the quantum mechanical ground state, and you may have some symmetries. Okay, so there may be some operator that some unitary operator that implements these symmetries, leaves the Hamiltonian invariant, and the question is, when you have such a setup, what kind of new physics do you get? Okay, which is not available in the limit of small number of particles. Okay, and of course we know that one of the consequences is we get phases of matter. Okay, so if you were to tune this Hamiltonian, vary some parameter, it can be in different states, and there are certain different states where there is no way to go smoothly between them. Okay, let's say you keep, in some cases you need to preserve the symmetry, so you sort of break up your parameter space of this Hamiltonian. So imagine you have some parameter space, okay, and you break it up into some regions. Let's say there's a region here and another one here, so let's call this phase 1. Okay, and when you go from one phase to another, let's say you go from phase 1 to phase 4, something singular happens. There's some phase transition, and there's no way to avoid that. Okay, if they're really distinct phases of matter, there's no way to avoid that, and we'll see an example of that in the 1+1 dimensional Ising model, but this is the familiar phases of matter just taken into a quantum context over here. Okay, so there are different ways in which phases of matter can be distinguished. The simplest, which is on the basis of symmetry, okay, so here the symmetry can be either broken or unbroken. Okay, so a magnet, for example, breaks time reversal symmetry and breaks the orientation symmetry of the spins in the high temperature phase or in the paramagnetic phase. Symmetry is restored. So that's the usual sort of paradigm, the Landau paradigm for getting different phases of matter. So Lucas, in his last talk, he told you about phases of matter that are distinguished on the basis of topology. Okay, so these are, for example, things like the Majorana chain, okay, the quantum Hall effect, okay, and so on. The fractional quantum Hall effect too. Okay, and what we have learned more recently, so this is very old, of course. This is fairly old, from the 80s and 70s and 80s. And what we have learned more recently is that you can combine the two. Okay, and there's a lot of very rich physics when you combine symmetry and topology. So to define this kind of topological phases, you don't have to appeal to any symmetries. Okay, so for example, if you were looking at the Majorana chain, this is a chain of paired electrons, or paired fermions. You don't have to invoke any additional symmetry. It's simply the conservation of the, you cannot change the total number of fermions by 1, right? You cannot just add one fermion to the universe. They always come in pairs. So that's the only kind of input there that gives you this, the Majorana zero modes. Similarly, if you had the fractional quantum Hall effect, there are interesting interplays between the charge conservation and the topology, but for the existence of the phase itself, you really need nothing more than simply topology. Okay, so those are examples of phases that are entirely distinguished from trivial phases on the basis of topology, but then you can combine these two together, and you end up with phases like, for example, the symmetry protected topological phases, SPT. Okay, which we'll talk a little bit about. Okay, so in all of this physics, these ingredients are important, large number of particles and so on. But there's one ingredient which is often not stressed and which we'll try to stress during these two lectures, which is this Hamiltonian that we pick. It's a Hermitian operator, of course, but it's very important that it it satisfies certain physical conditions, the most important of which is that it is local. Okay, so the interactions that appear in H, they respect the fact that the degrees of freedom are actually embedded in a space of certain dimensionality. Okay, there's a notion of which spin is close to another spin and which ones are far away, and this is reflected in what couplings appear in your Hamiltonian. And for example, the simplest way to implement locality is to say that a spin only interacts with its near neighbors, maybe just nearest neighbor interaction. Even if you have longer range interaction, there should be a distinction between spins that are far away, so there should be some fall off of your interactions and really reflect the fact that you live in a particular dimension. Okay, the dimensionality of space only makes sense if you have certain notion of locality in your Hamiltonian. Okay, and we'll see that this is going to be very important when we talk about phases of matter. For example, the fact that this model over here will have two phases will depend in a very key way on locality. Okay, and really that is what ends up giving you these different states of matter. It may seem that when you're in this situation, you have no symmetry, you just have a Hamiltonian. How come you end up splitting up states into different phases? Okay, and ultimately it's all controlled by the fact that these are ground states of local Hamiltonians, and if you preserve locality, if you don't allow for arbitrarily long range interaction, then there can still be distinctions between states of matter. Okay, so to give you a very quick example, just I see some sort of skeptical faces, but if you think about the Majorana chain, I'm sure all of you have seen this before. You have a superconducting chain with these zero modes at the ends, Majorana zero modes. These are exactly at zero energy, and the way you argue that they are at zero energy is they can actually split. If you had a zero energy mode and it comes in contact with another zero energy mode, the two of them can repel each other and end up splitting. But you say there's no other zero energy mode nearby. Okay, the only other zero energy mode is at the other end of the chain, and then you appeal to locality. Okay, you say that if you have these two zero modes, they could interact, but the interaction is going to be extremely weak because there is a gap in the bulk and all the interactions are local. Okay, and they cannot really see something that's very far away. Okay, so when you establish that this is a separate phase controlled by the fact that these modes are almost or at zero energy, you're appealing to the fact that you have a local Hamiltonian. Okay, so I'll try to emphasize that as we go along, but that's kind of one of these hidden assumptions that it's sort of hard to write down. It's very easy to tell you that there's a symmetry, but locality requires is a little less compact in order to write down as a condition. Okay, so that is sort of by way of introduction. Yeah.
This notion of locality and gap Hamiltonian, are these really equivalent, or you can have
no.
Gap? But
That's a good point. Yeah. So the Hamiltonian, so the locality in H is just a statement that the couplings in H, you can write it in terms of some some sum over some terms, each of which only involves a finite number of spins. And at this point you do not, adjacent spins. And at this point you do not require that this is gapped or not. But over here in this argument, I think the reason your question is coming up is when you make this argument, there are two ingredients. One is that there's an energy gap, and the second is that there is a local Hamiltonian. But they are actually separate ingredients. I'm just saying that the locality is a necessary condition for the zero mode to exist. It's not a sufficient condition, of course. You also need the gap. Okay, so we have all of these interesting phases. You also have phase transitions between these phases. We'll talk about a phase transition where symmetry is broken, or if you like, topology is changed. when you describe these phases and try to describe the phase transitions, you have certain choices in terms of what variables you use. Okay, and you can make your life very easy or very hard depending on those choices. Okay, so really what this duality we'll talk about is, one way to think about it, okay, its utility is you help okay, so whether it's describing a phase or a phase transition, sometimes you can make your life easy by finding the right variables. Okay, and we'll see an example of that where it really works out very well in one dimension. Sometimes this notion of right variable may actually depend on what question you're asking. Okay, for certain questions it may be well posed in certain set of variables and not so in a different set of variables. Okay. Okay, so there are a bunch of different dualities that people have been talking about. So one of them is a duality from a bosonic system to a different bosonic system. So we'll be able to find an example of that in this 1+1D Ising model, okay, where this will actually turn out to be going from the spin variables. That's one are the variables in which the model will be defined to domain walls. Can turn out these domain walls are also bosonic degrees of freedom, if you like, and interestingly, in the one-dimensional case, in the 1+1 dimensional case, the two theories will look essentially identical. Okay, so there'll be a self-duality whether you describe it in terms of spins or domain walls. It turns out this is related to the famous Onsager duality, discovered or the Kramers-Vanier duality, okay, which was discovered in the StatMech context. So that was 2 dimensions, but StatMech, so 1+1D quantum is the same as 2D StatMech, but it will be much easier to do this in terms of in the quantum model, actually, it turns out. And what is there's a reflection of this in 2+1D, but now you need to have an XY model to change the symmetry. This has a U1 rotation symmetry. And here the duality will be between bosons, or again spins if you like, and vortices. Okay, and there's a lot of activity talking about dualities in 2+1D. This is sort of the basic one. In condensed matter, it was discovered by Halperin and Dasgupta. Okay, and there's also a bose-Fermi duality. Okay, so you can rewrite the theory in terms of new variables, which are now fermions. So there's a lot of interest in 2+1 dimensions right now. These fermions are sort of bound states of bosons and vortices. Okay, in a certain sense, and it turns out in one dimension there's an analog as well. It's a bound state of the spin and the domain wall. We'll construct that explicitly. Okay, and it'll turn out that these are actually the right variables to describe the 1+1D Ising model, okay, these fermions. So the aim will be to get to this point, and you'll see why this particular kind of duality is extremely useful. Okay, so that's again a bit of outline. Okay, and then finally, for SPT phases, we'll see that we can use this. We can take 2 copies of this Ising model in one dimension, perform the duality on one of them. So one example of a SPT phase in 1+1D is 2 copies of the Ising model. Let's call that Z2 times Z2. It's 2 Ising models, and we'll do the duality on one of them and not on this, and take the bound state of these 2 objects, the spin and domain wall. We'll condense them. I'll try to make this more precise, what we mean by condensing an object, and that will end up giving us this SPT phase. Okay, so and this is the kind of the variables in which we'll describe not just the single Ising model, but also this one, which is a pair of Ising models. Yeah.
How important is low dimensionality? It seems like you could keep going.
Yeah. Yeah, so one thing you notice is I changed the symmetry of my system as I went up. So if you went to 3 plus 1D, the natural thing to do is to go to a Heisenberg model. And that, so the key question will be that in these cases you see that this is a domain wall, which is sort of the defect of your ordered state. This is a vortex. So the question will be whether the defect that you're interested in is a point particle or not. So if you did domain walls in 2 plus 1D, they would be extended line objects. If you did vortices in 3 plus 1D, they would be line objects. And those would be hard to describe with a field theory. So that will be sort of important in this these discussions. Okay, so okay, so let's discuss this quantum Ising model. Actually, maybe let me write it up here. Okay, so we're going to think of the simplest site Hilbert space that you can possibly have, which is just a two-level system. So you have two states, and it's convenient to think of them as spins because we're going to give them a symmetry very soon. So let's say on each site, so I have a chain composed of these two-level systems. Okay, so there are n sites. And every site is the absolute simplest quantum mechanical system you can think of. Okay, there are exactly two states. Let's call them up and down. Okay, and you can write down some operator for which this is the eigenstate up and down, plus minus up down. Let's call that the z component of the spin. You can also diagonalize it on a different basis, sigma x, let's say. Okay, I'll call this spin pointing sideways. Okay, so hopefully this comma notation is clear. Sigma z acting on up. Actually, let me write it down separately because it looks like this is a tensor product of the two things. So let me not do that. Okay, but then you can also define these objects, which are the linear combination of up and down. Okay, so we have these Pauli operators at our disposal, but on every site. Okay, and we're going to take eventually the number of sites to infinity. So what is the Hamiltonian for our model? Well, we have some choices. Okay, so we're going to demand a few physical requirements. The first, of course, is locality. So I want only sites that are near each other to interact. The other thing we'll impose is a symmetry. Okay, so we'll impose a Z2 symmetry. So let me write down an operator that sort of physically imposes the symmetry that the up and the down states are sort of symmetric with one another. Okay, there should be no explicit distinction between the spins pointing up and the spins pointing down. Okay, and of course, for that you need an operator that will flip the spin. So it will take a state which is spin up and flip it to spin down. That implements the symmetry. And if you just from your knowledge of Pauli operators, sigma x, for example, does that. Okay, so the symmetry is going to be just sigma x on every site, so you have to take the product over all sites, the sigma x. Okay, and this operator, it's a unity operator, and it squares to unity. Okay, so the group formed by this, the symmetric group is just two elements doing nothing, the identity, and this operator G. Okay, so obviously this is a Z2 group, two elements. Okay, so we'll call this sometimes Z2 symmetry. So these are the two conditions we want. We want the Hamiltonian to be local, and we want it to respect the symmetry. Okay, and strictly speaking, you should, if you want to study this in general, you should allow for various interactions that respect just these conditions. Okay, so in physics, in a realization of of this 1 plus 1D Ising model, you have some complicated material that realizes this. And in principle, all kinds of couplings are allowed as long as they're local and they respect the symmetry. Okay, but sometimes just to make progress, we'll write down a specific model, and I'll try to tell you what is specific about this model and what is general. Okay, so we want some symmetric, kind of coupling. So of course, I can take sigma x. Sigma x itself commutes with G. It doesn't distinguish up and down spins, so you can always have a term that's sigma x. Okay, but I also want something that talks to the sigma z's. For example, I may want these spins to have an interaction that favors some ordered phase. Okay, that favors all the spins to point in the same direction. So you can do that with the sigma z term. Okay, there's an overall negative sign, some coupling that is J that is positive, with the minus sign in front that tells you these spins want to align parallel to one another. And this term is also symmetric. If I picked only one sigma z, that breaks the symmetry, of course, that picks up versus down, but this treats them in a democratic fashion. Okay, it tells you the spins are parallel, you get one energy. If they are anti-parallel, you get a different energy. Okay, but it doesn't break the symmetry of up and down spins. Okay, and you can check it commutes with this symmetry operator. Okay, so this is a model we're going to work with, sort of a nearest neighbor Ising model, and it has this Z2 symmetry. Okay, so we'd like to figure out how this model behaves as I vary parameters. There's only one really relevant parameter over here, which is the relative strength of these two couplings. Okay, so I'm interested in the ground state of the system. So really this overall energy scale does not matter, but the competition between these two terms, you see that these two terms do not commute with one another. Okay, there's sigma x, sigma z, they do not commute, which tells you that you cannot satisfy them both at the same time. If I simply just if I try to satisfy this, I end up paying a penalty over here and vice versa. Okay, so that gives you something interesting that's going to happen in this model, and we can try to sketch a phase diagram. Okay, so there are two limits you can study this problem. So you can look at the G going to infinity limit, or G large limit, where basically what you want to do is you want to make that sigma x term happy. So you want a state where sigma x on every site is +1. Okay, and so that is achieved if you were to put every spin in a state which looks like this, in this sigma x eigenstate. Okay, so there's a unique ground state in this limit where every site is in the sigma x eigenstate. Okay, so I'll also represent this by a string of zeros. I can also think of this as qubits if you like. Okay, so we can define 0 is the sigma x equal to +1 eigenstate, and 1 is the -1 eigenstate. Okay, that's another piece of notation which is sometimes useful. So you can think of this state as a vacuum. Okay, there's a state which has no ones in it, all zeros, that's like a vacuum. And what's going to happen is that this term is going to start inducing fluctuations of this vacuum. Okay, you're going to get creation of pairs of particles, and that's going to give you a more interesting structure to the vacuum until eventually you figure out what happens in the limit where G is small. Okay, so let's try to study that in a little more detail. Okay, so we said that we have the ground state of this Ising model, the string of zeros, but it's actually interesting to also ask about the first excited state. Okay, so we said before that we're going to be interested just in ground states, but what's going to happen is that the excited state that we'll talk about now, as you change parameters, that's going to come down in energy and eventually mix with the ground state. Okay, so it will help you understand the ground state somewhere else in parameter space. Okay, so so let's try to understand that, starting from this limit. So we have the ground state, and we want to find the first excited state. Okay, so what is the first excited state in that model? If I'm I think I couldn't hear you, but I think you did something with your hands, which I think means you take one of the spins that's like this and flip them over to that, right? So you take a single site where sigma x is +1, and flip it over to sigma x equal to -1. Okay, and you're going to pay an energy cost because G is large, and that's penalizing sigma x equal to -1. So there's an energy cost delta E, which is 2 times J times G. Okay, it was -1 to begin with. It was happy. It was minus JG to begin with, and then you made it plus JG, so that's 2 times JG. Okay, so in this other representation, you took a 0 and you created a 1. Okay, you flipped, you inserted a particle, if you like, into the sea of zeros. Okay, so if you look at the spectrum, there's a ground state, and then there's an excited state. Actually, there are many excited states. Okay, they all at 2 JG. Okay, but these excited states, you can label them by the integer n where this flip spin occurs. Okay, so this n is a string of zeros, and there's a 1 somewhere at location n. Okay, so if I just restrict my attention to this space of excited states, the first excited states, I can label them by this integer n. Okay, it's like a 1 particle state. Okay, and what you can do now is you can ask this was just looking at this term in the Hamiltonian. Okay, but we're interested actually to know what does this term do. It's weak because G is very large, but what is the perturbative effect of this term over here? Okay, so any suggestions what that might be doing? Yeah, it moves that around. Okay, so if I take a state n and I take the operator sigma z, okay, and for example, look at the overlap with a neighboring site, you can think of these sigma z operators as sigma plus and sigma minus in the sigma x bases. Okay, similarly for this one. Okay, so there'll be a term there which will kill the particle on this site and move it to the next site. Okay, so this will be, unity, I guess, if this I is some bad notation, but Okay, so if you work this out, if the effective Hamiltonian in this one in the excited state, okay, so let me call that H1. I'm only going to consider states in this manifold over here and look at what the effective Hamiltonian is. Well, there is a hopping term which is this J times okay, which will hop me from site n to n plus 1 if you like. There's some sum on n. And then there is an energy cost which is simply independent of where these things are, which is twice Jg. Okay, so this looks like a tight binding model hopping of a particle on a chain. We know how to diagonalize this. You go to Fourier space, you rewrite these, you define these plane wave states, k, which are just Fourier transforms of this position state, okay, sum over all n, the state n with a particular phase factor. And in terms of those variables, you get diagonal Hamiltonian, which is twice j cosine k. Okay, so for each momentum, you get a Hamiltonian, which is just this. Okay, so basically what this term did was to take the degeneracy that you had and reorganize that in these momentum variables, and it gives you some dispersion that looks like this. Okay. And this bandwidth over here, so this center was twice Jg. Okay, and you know, this bottom over here, or this this thing down here is twice Jg minus twice J. Okay, where the cosine is 0, sorry, where k is 0, cosine is unity, that's the bottom of the band. That's of course the center of mass minus this kinetic energy. Okay, so of course this is done in the limit where G is very large, so this is still very high above your ground state. But one thing you could do is to blindly take this calculation and extend it you know, even to small g, right? So that's not quite kosher, because when you do that, you start getting multi-particle states and so on. You cannot just focus on the one excitation state. But let's just do that, and what you see is that if G is 1, this energy gap will close. Okay, and these excited states will come and start mixing with the ground state. Okay, so we'll call that condensation. Okay, so it looks a lot like Bose-Einstein condensation. You have some excitations, and you kind of bring the chemical potential up to meet those excitations. Okay, and then they'll form a condensate. So in this case, the thing that's condensing are these spin flips. Okay, these ones are condensing. Okay, and so you really, to understand the small g part of the phase diagram, you really have to understand how these spin flips, when they mix with this ground state, what is the state that they produce. And we'll see that the state that they produce is actually the broken symmetry state. Okay, the ground state that you get for G less than a certain critical value, the estimate is 1 over here. You shouldn't trust the estimate, because you know, it was a sort of crazy extrapolation. Turns out that answer is correct for completely like fortuitous reasons. But below some critical G, say G equal to 1, the system enters a state where, although it has a symmetry in the Hamiltonian, the ground state breaks the symmetry. Okay, and the symmetry breaking only occurs in the limit of very large number of sites in your system. Okay, so so let's kind of discuss that part of the phase diagram now. The limit of G being you know, very small. Okay, so to understand that part of the phase diagram, it's good to go all the way, go to the point where you can simply neglect that sigma x term. Okay, so now my Hamiltonian is essentially Okay, and if you take this Hamiltonian and diagonalize it, of course what you want is you want adjacent spins to point the same direction, but now along z. Okay, so you changed our basis over here. So that's a state that does that for you. All the spins are aligned, but there's another state that's equally good. Okay, and these are degenerate. Okay, and of course if you apply the symmetry operator to this G, big G, it will take this state over to that one. Okay, so they're related by symmetry. Okay, so now of course if you had any amount of little g present, you would get quantum fluctuations. In a quantum mechanical system where n is finite, every eigenstate has to be, if you have a symmetry of the Hamiltonian, you should be able to label the eigenstates by eigenstates of the symmetry operator as well. Right, this is an operator that commutes with the Hamiltonian. Okay, but so if you had a finite system, you would of course get superpositions. Okay, either plus or minus the state with all down. Okay, so this is a finite G and finite N. Okay, but if you go to the limit of infinite number of particles, a very large number of particles, you see that this is an extremely strange kind of state. It's actually a Schrodinger cat state. Okay, all spins being up plus all spins being down. If this was one spin or two spins, that would be fine. But if you have a macroscopically large number of spins, it's kind of like having a cat which is dead and alive. You have a system that will have a macroscopic magnetization up or down, and you're asking to put that in a superposition state. Okay, so we don't allow such states. Okay, so let's say by hand I kill all these kind of Schrodinger cat states. No cat states, let me call it. Okay, in the limit of n going to infinity, that's where you kind of utilize n going to infinity over here. Yeah, and then you're forced to decide whether you're all up or all down, and then the ground state breaks symmetry. Okay, so in other words, you cannot label the ground state by eigenvalues of G. They're not eigenstates of G. Okay, so there are more physical ways of doing this. This is kind of an entanglement kind of way of kicking out these states. You can also think about putting on a small magnetic field that breaks the symmetry, but then you imagine keeping that field present, but extremely small. Take the limit of n going to infinity, and you'll see that you can have even an infinitesimal field, and you'll favor one or the other state. Okay, so then you can more or less ignore the field, switch it off, and you'll end up in these broken symmetry states. Okay, so I won't go into too many details of breaking symmetry in a quantum system. It's pretty subtle actually, and it's worth thinking about. But for our purposes, what we need is that in the small g limit, you can argue that what happens is that this Z2 symmetry is spontaneously broken. Okay, so it's broken by the ground states of this this Hamiltonian. Okay, so we can construct a phase diagram now. Okay, so there's some critical G. Okay, so here roughly the caricature of the state is all zeros. Over here the caricature of the state in this region is all spins up. Okay, so you break the Z2 symmetry. Okay, another way we talked about this state is a condensate. So when you say that there's a fixed phase between these two states, That's a complete fiction, right? Let's imagine you try to measure this phase. You have a system with all the spins up or all the spins down, and you want to. And I told you initially that there is a plus sign between them, and this sign is completely kind of key in order for it to be an eigenstate of G. So if you're not able to assign physical meaning to the sign, in other words, if you're not able to measure the sign, it makes no sense to talk about this covariant superposition. Okay, so now let's imagine trying to measure this sign. Okay, so what would you have to do? You'd have to take a system which is kind of in a quantum superposition of all the spins up plus all the spins down, and try to do some interference experiment. But if I have a system which has a macroscopic magnetization, all spins pointing up, versus all spins pointing down, it's going to entangle with the rest of the universe in different ways. Right? It's so there's an environment, and the environment can tell that there are two different states. One has all the spins pointing up, the other has all the spins pointing down. It's not like a single spin where it's spin up plus spin down. Okay, where you could say that there is no macroscopic variable that distinguishes the two. So really, if you like, there's a classical variable that distinguishes these two. So you should not expect a quantum phase between them. It's just sort of the same thing as the Schrodinger cat sort of paradox. For a macroscopic system where you can actually tell the difference in the state macroscopically, it doesn't make any sense to assign a phase, a superposition to the two states. Yeah, but this is a bit it's a bit subtle, but you kind of there are these notions of cluster states. So when people talk about clustering properties, there are certain properties you'd like to assign to nice many-body states. So for example, if I take a correlation function of two local operators, and these operators are separated by some large distance, then you expect that correlation function should reduce to the individual expectation values. That's sort of the definition of a cluster state. And that turns out to be the same as requiring that there aren't these sort of Schrodinger cat superpositions.
Also, some decoherence would happen faster than any sort of thermodynamic measure.
Yeah, that's another way to say it, yeah. But you don't have to take this point of view. You can just think of it more physically as apply a field. That's the usual way in which we think of symmetry breaking. Apply a field, and then you pick one or the other state. And as I vary the field, you go from one to the other. There's kind of like an S-shaped curve. But this curve becomes more and more narrow the larger the number of spins. So eventually you kind of get a situation where you sort of switch between the two. And then you can have an infinitesimal field, and you're in either one or the other ground state. That's kind of the physical way of saying that you have symmetry breaking. Okay, so I haven't got to duality yet, which is, but okay, so we have this picture of all of these zeros. So what happens in our picture is that you have these zeros, then this excitation which has the ones in it comes down in energy and starts mixing, and then eventually it's one way to. So right now I've written the ground states, but I've written them in different variables. Okay, so how do you kind of go from here to there? Basically what happens is that your state 0 goes to a superposition of 0 and 1. Okay, that's like a simple caricature of this ground state. Okay, and when you do this, you actually break the Z2 symmetry. Okay, so if you ask what is the expectation value of this state, let me call it phi. If I look at the expectation value of sigma Z in this state, okay, this is proportional to phi itself. Okay, so if you like, when I pick a phi, I either pick it to be plus or minus positive or negative number. You end up choosing sigma Z to be either up or down on average. Okay, so an exercise maybe I'll leave to you is, think of this as a variational state. You have a state that has one parameter phi. Just imagine that this parameter is independent of which site you're on. You have a product of these states, and you can try to minimize the expectation value of the Hamiltonian with respect to this phi. And you'll also find again this phase diagram. It takes a finite region over here. Initially you prefer the state which has phi equal to 0. that's just the state over here. But beyond a certain point, when G becomes sufficiently small within the energetics of that variational state, you end up preferring some value of phi. Okay, and this value of phi grows, and eventually it gives you this state over here. Okay, so I'll leave that as an exercise. That's called mean field theory. So determine this phase diagram using mean field theory. Okay, this will be in the notes, so you can refer. Just look at the expectation value of the Hamiltonian in this variational state phi and minimize. Okay, so that is one way of looking at this problem. So now let's try to do the whole thing in a different way, which is actually the dual picture, and you'll see that it's very analogous. Okay, so we talked about the excited states and this G to infinity limit. Let me do the same thing, but in the G going to 0 limit. Okay, so let's repeat this problem. Okay, so I'd like to understand what now we figured out what the ground state is. So now let's figure out what the excitations are. Okay, so the ground state we said was all up or all down. That's at least the limit of G going to infinite of G going to 0. Okay, and I want now the first excited state, just like I had before. Okay, so what is the first excited state for this problem when I have the small g limit where all the spins are either up? Let's say I pick this ground state. Yeah, so unfortunately all of you gave me the right answer. I wanted to hear the wrong answer, which is the spin flip. That's the most natural thing to do, right? You do the same thing that you did before, just go and flip the spin. And that has an energy of 2 times J. Okay, so you pay an energy cost for this, this pair of spins being, okay, so let's say someone gave me the answer that it was this, right? This was the excited state. Then you mess up this bond and you mess up that bond. Okay, so there's an energy cost of 2 times J over here, 2 times J over there. You'd get an energy of 4 times J for this excitation. Okay, but you can do better than this by you flip the spin over, but keep doing that, keep flipping with these spins over. Let's say I have open boundary conditions, and you can do better than this 4 times J. You can have no bad bond now except this one over here. And so there's an excitation at 2 times J, which is the domain wall. Okay, where basically you go from one ground state to the other. Okay, so that's very typical of a topological defect. So you have some broken symmetry state, you have multiple vacua, multiple ground states. So these ground states all have the same energy density. Okay, if you look at the energy per site, by symmetry they are the same. So what you can do is you can take one state in one part of your system, another state in a different part of your system. You know, the energy per site is going to be the same as having just one state, but where they meet up against each other, there can be some surface energy cost. Okay, but that is of course small if you have in a one-dimensional system. It's just it's like an excitation energy. If you did not have the symmetry, this would be an extremely high energy state. Okay, if this was, let's say, a slightly higher energy than this one, then for every site you're going to pay an extra energy cost that's going to grow as you make your system bigger. Okay, the reason this is a low energy state is very crucially dependent on having the symmetry. That this and that taken by itself are ground states, and it's only when they meet that you get an energy cost which is 2 times J. Okay, so the excitations on this side of the phase diagram as well, you can think of them as particles, right? These particles really live where you go from uniform spin in one direction to uniform spin in the other direction. And you can try to develop a theory of these particles very much like you did for the spin flips. Okay, the important distinction over here is this is a non-local object. Okay, if you start in a ground state and you want to create this, you have to flip all of these spins over. The entire string of spins have to be flipped over. So if you do a physical experiment, for example, people do neutron scattering on these systems, what they can do is they can flip a spin. A neutron can come in and flip a spin. So you can create those spin flip excitations we talked about before, but a single neutron cannot create this excitation. Okay, so if you do a neutron scattering experiment, this is actually invisible, you don't see this. The first thing you see is up there where you get pairs of these domain walls. Okay, so there's a physical distinction between them, between these two kind of states, the domain wall versus the spin flip, but we'll see mathematically they're extremely similar. Okay, and we can develop a dual theory. Instead of describing everything in terms of the location of the spins, what the spins are doing, we can write down a theory where I tell you where the domain walls are and what the domain walls are doing. Okay, so if I give you a spin configuration, okay, of course that is, that specifies the state of your system. I tell you which spins are up, which ones are down. But there's another way to specify the spin configuration, which is, say I tell you what the first spin is doing. Okay, I tell you that the first spin is up, and then I tell you the locations of the domain walls. I tell you there's a domain wall over here and no other domain walls. Okay, you can deduce the state of all of the spins just from that information. Okay, you know that there's a domain wall over here, so the spin has to go down. There are no more domain walls, so it stays down. Okay, so there should be a way of trading my spin variables for domain wall variables. I may need one more extra bit of information, but I'm thinking about a large system, a large number of spins. I don't really care about one bit of information. There should be essentially a nearly complete specification of my system in terms of domain walls. Okay, so to develop that further, let me sort of write down the analogy between spin flips. Okay, so what really are we after to make this more precise rather than drawing pictures? So at spin flips, we said that we have this state 0 and it goes to a spin 1, goes to 1. Basically the sigma x eigenvalue is different. Okay, so sigma x went from +1 to -1 in this process. Okay, so what is the operator associated with spin flips? Okay, we have a physical picture of spin flips. What is the operator content of the spin flips? Okay, so there's really an important distinction over here. So when you talk about an excitation, there are two kinds of operators. Okay, there's one that measures the excitation. Okay, so there's a measuring operator. This is sort of like the number operator. Okay, if you had bosons or something, you'd have a number operator that measures how many bosons you have. That is this operator sigma x. Okay, so essentially sigma x measures whether you have a spin flip or not. Strictly speaking, if you have this, you want this to be 0, so you say 1 minus sigma x over 2 is like a number operator. Okay, and this will give you either 0 or 1 depending on whether sigma x is +1 or -1. Okay, so that's one set of operators. There's another set of operators which is the thing that actually creates or destroys these excitations. Okay, so creation and destruction operators. Okay, so these are sort of like your B dagger and B operators. If you had a boson system, the thing that's special about our problem over here, we have like a Z2 symmetry. Okay, there's no distinction between creation and destruction. You create something or you destroy. You can create things in pairs basically without any penalty. So the thing that does this is actually the sigma Z operator. Yes, sigma Z is going to take the 0 to the 1. Okay, it flips the state of this thing. So if you like, it's like a creation operator. It creates 1. It also takes 1 to 0. So it's also like the destruction operator. Yeah, so what we want to do is to write down a dictionary with analogous operators over here for these domain walls. Okay, so okay, so what is the operator that measures whether or not we have a domain wall? Okay, that's the first question. Okay, so I have domain walls. Let's say I have all spins up and I have all these spins down. I want an operator that measures these domain walls, okay, where I have a domain wall. Okay, any suggestion for this? Yeah, so it's just a pair of sigma z's, so it's just sigma z I. Okay, and this object is either +1 or -1. It's measuring whether there's a domain wall or not. So by analogy, let me call it mu x. Okay, so we saw before that it was the x spin operator that measured whether or not I had a spin flip. So let me call this the x component of some other spin, some other object that now lives, strictly speaking, on the bonds, right? This domain wall is really associated with the bond, the midpoint between the two sides. Let me label it as I plus half. Okay, so that measures whether or not you have a domain wall. Okay, what about creating a domain wall? Creating or destroying a domain wall. It's a string operator, so you want to take all the spins, let's say, to the right. There's some choice over here. I'm going to take the spins to the right. I have open boundary conditions. So you take the product of all the spins to the right of some and again by analogy, let me call this mu z, thing that creates or destroys a domain wall. Okay, so one thing you notice is so if I had if I just wanted a sigma x, let's say at the site I, what I could do is I could take a pair of these mu operators. So pictorially, this mu operator over here is a string that flips all of these. You can take another mu operator that flips all of them. You flip things 2 times, you get back to where you were. So this operator that flips just a single spin is simply a product of this domain wall operator at the site before and the original site. Okay, that product leaves only one sigma operator untouched, which is the sigma x that I want. Okay, so you can see that there's a distinction now. These kind of look like the algebra of my original spin flips, but this is a non-local operator. When I try to create a domain wall, I've got to flip an entire string of spins. Okay, so physically they are different, but they look very similar, right? You still have, these are also Pauli operators. Do them twice, they go back to the identity. So they have the same algebra as the sigma operators, and we can try to rewrite the Hamiltonian in terms of them. Okay, so we have found these domain walls. Okay, I'll just do this and then I'll end. Okay, yeah. So let me try to rewrite my Hamiltonian. I had my Hamiltonian in terms of the original spin operators up there. Okay, so dropping some indices, etc. I had this. Let me rewrite in terms of these variables. That's easy to do. Sigma x. Well, I just figured out what sigma x was. It's the product of these things, right? Okay, so this becomes g times mu z I minus half mu z I plus half. Okay, and the product of sigma z is, well, that's just the domain wall measuring operator, x. Okay, there's someone I. I'm not being very careful with boundaries, and that's sort of, there's some subtleties with respect to the boundary conditions and so on related to the fact that I need one spin to tell me the overall spin configuration. Let me ignore that for a second. And let's look at compare these two Hamiltonians. Okay, so they have exactly the same form. Right. I just traded sigma for mu, and the roles of these two terms flipped. So now this term is now the measuring term, and this is the the z term, and this, if you like, I could take out this g. I said the overall strength is not important of this coupling, and I can get a 1 over g over here. Okay, so basically g went to 1 over g, and that is really a sign of duality. It took this is sort of the coupling constant in my theory. You took a coupling constant G and you went to the inverse coupling constant. So things that were at strong coupling, if you like, are now at weak coupling, and vice versa. Okay, but the thing that's special about the Ising model, which is somewhat rare, is that the form of this dual theory is exactly the same as my original theory. Okay, so this is self-dual. Okay, and I had such an easy time partly because I just restricted attention to these nearest neighbor couplings. You could have had further neighbor couplings. That would look a little more ugly when I do this duality, but in some sense your the physics is somehow still self-dual in the sense that you have these two descriptions, right? You have spin flips. These are point particles that interact via some local interaction, or you have domain walls. These are again point particles which interact via some local interactions. So effectively they kind of look very similar, and some effective theory for either of them would have very similar kind of features. Okay, and later we'll see that there's another set of variables you can write down. So this hasn't actually simplified the problem for us. You have the same problem coming back at you. One thing you notice is that G equal to 1 is special. Okay, it maps back to itself. In fact, that's where the transition is located. You can argue that this duality fixes the location of the transition. Okay, but it doesn't do very much else in terms of giving you information. It gives you a nice picture of all of the phases. You can think of the ordered phase over here as the phase which has no domain walls, the vacuum for domain walls. The vacuum over here is a domain wall condensate. But apart from that, it doesn't do very much. But there's a different set of variables that we'll write down, the fermions, where it'll actually you'll be able to solve the problem exactly. Okay, and that's really the right set of variables to discuss this problem. But okay, that's for the next lecture.